Okay, so hi, my name is Catherine, and this is my project, Galaxies Far, Far Away. Okay, so nowadays, scientists are more looking into space, like with the James Webb Telescope, and there's so much data coming from that it's getting kind of hard to look at that and organize that. So with my project, it uses a convolutional neural network to classify galaxies in the Galaxies U2 data set and to achieve high accuracy in classification. So neural networks are popular for recognizing and classifying objects and images. Common uses are video surveillance, self-driving vehicles, and cancer screening. The goal of my project is to apply this capability for the purpose of identifying galaxy types in telescope imagery using a neural network. So convolutional neural networks make up the first layers of the neural network intended for image recognition. The output of a CNN layer is typically connected to a max pooling layer, creating what is referred as a feature map. The layering CNNs and max pooling layers provides a broader neural network with the capability to recognize more complex image features. So yeah, I got the images from Galaxy Z2. It contained over 200,000 images. The images came from the Sun Digital Sky Survey telescope. The data set was in color, 424 by 424 resolution, JPEG images along with 2 spreadsheets for referencing each image's classification, which was very useful. So the different types of galaxies are ER, which is basically elliptical, so it's a smooth galaxy completely around. The SBZ2M was a bar disk galaxy with just a noticeable bulge, and 2 medium spiral arms. SCB was an edge-on disk galaxy with a boxy bulge. SCL was disk galaxy with just a noticeable bulge and a spiral structure or irregular morphology. And A was star. For this project, the classes were reduced to 3, which were elliptical galaxies, spiral galaxies, and edge-on spiral galaxies. Stars and galaxies with irregular features were not used in the training. The software was developed using the Python programming language running with Anaconda. Python modules used the following. OpenCV, that was for loading images, changing it to grayscale, and saving them. Scikit-image was for finding the intensity contours in the image. tkinter was for creating the GUI, and that helped a lot. NumPy was for a list in the math. Pandas was for reading spreadsheet files. Matplotlib was for plotting data. TensorFlow 2 is for building and training and testing the CNN. OS was used for image directory queries. Random was for image name shuffling. And yeah, that's the hardware for the PC. Okay. Galaxy images were converted from 3D RGB, otherwise known as red, green, and blue, to 2D grayscale. This resulted in 224 by 224 pixel images with intensity values ranging from 0 to 255. Of the many contours generated by this function, the contour with the largest length is chosen since this most likely encloses the galaxy of interest. And then you find the contour point that is farthest away from the galaxy center and use that to find the radius of the circle enclosing the galaxy. And then you create a filter image with a circle of this radius where inside pixels have value 1 and outside pixels have value 0. Multiply the corresponding pixels in the image and the filter to remove objects outside the circle. So yeah, that's the normal image. And the contours, you can tell which one is the galaxy that was the longest one that there was that I had it pick, and it just got rid of all the rest and like put like a circle around the galaxy radius. And this is an elliptical one, same thing, and you still got a lot of junk, and then you have it pick the longest one, and sometimes that would mess up, so it's not fully perfect. And yeah, some of these images had a lot of stuff, and in the beginning, without pre-processing the images, the neural network would get confused at what it was looking at. Okay, so this is the CNN model. So you first have, the first layer is the pre-processed image, followed by 3 convolutional layers with max pooling. And then you get to the flattened layer, followed by 4 dense layers. And then the last one has 3 neurons, which are for the classification and what it got. So yeah, spiral, edge-on, and elliptical. Okay. Convolutional layers were set to use 3 by 3 filters. Max pooling layers used 2 by 2 filters. All activation functions were of the ReLU type, and the final layer used softmax to provide the confidence value. Experimentation was then performed by varying the sizes of the layers and noting the performance of the CNN's training accuracy and validation accuracy. The CNN was created using TensorFlow 2 module, and its Keras wrapper available to Python. Testing data is packaged into TensorFlow dataset objects. So yeah. Testing data is also packaged into TensorFlow dataset models with training and test data ready. The CNN model is created layer by layer using Keras. And yeah, you got the number of neurons in the dense layers. And before flattened, the numbers were set or like were changed. Were set to like were changed to like help the neural network. Okay. TensorFlow 2 arguments were passed to the compile function of the model object. Optimizer was atom, loss was sparse categorical cross entropy, metrics was accuracy. Epoch count was set to 30. Images were also cropped to 20 by 20 pixels. 200 by 200 pixels. Pixel values were converted from the original 0 to 255 range, 8-bit unsigned integer to a 0 to 1 range. We get 32-bit floating point. The pre-processed images were allocated in this way. So 80% with the training data set, that's the percent of the images they had a test on, training on. And then 20% went to the validation. The final model was trained and validated over a total of 60 epochs into 30 epoch runs. The first run resulted in the data shown in Figure 5. Training accuracy yielded 96%, with the validation accuracy 81%. So yeah, the training accuracy did very well, as you can tell. And the validation accuracy is pretty good, but it could be better, and it kind of messed up here and there. So in an attempt to improve the validation accuracy, a second 30 epoch training run was done, creating the result of Figure 6. Training accuracy improved to 98%, but validation accuracy declines to 79%. And it is an indication that the additional training was tending toward overfitting the data. So what happens is that the neural network gets too good at the training that it doesn't do so well when it sees stuff that hasn't seen before. The final realization of the Python program is an interactive graphical user interface, which is GUI. That's what it looked like. It allows the user to observe the preprocessed galaxy image along with its true predicted classification. The 3D plot in the creator provides, the center provides a topographical perspective of the image pixel intensity. Controls are provided at the bottom to load the image set, cycle through the images, and train the CNN. So yeah, that's what it showed when you have it load and train. Machine learning with conventional neural networks demonstrate a promising capability for the classification of galaxies in astronomical surveys. High training accuracies are demonstrably obtained with the convolutional neural network employed, but high validation accuracies were a bit more challenging to achieve. The use of custom developed processing methods such as the technique demonstrated in its high accuracy classification predictions. With the freely available data set provided by Galaxy Zoo 2, the free tools on Python, and any motivated machine learning developer who wishes to test their own pre-processing algorithm and neural network can try this challenge. And there are the references and the acknowledgements. So, yeah, I'm not sure how to show this on the thing.
You can try Window key and P.
You can also rotate the computer.
Yeah, or just
Yeah,
spin the
that
computer
makes
towards
sense.
us.
You had a link in your submittal that showed all the codes.
Yeah,
So I appreciate that.
yeah. So yeah, here's all the code. And it's very hard to see from all the way over there because it's just sharing onto the screen.
There's about 1,000 lines of code.
Yeah, and many. Yes, a bunch. So yeah, here. Here's what the GUI looked like, and yeah. So yeah, we got the many different images that it tested on this, and yeah, you can move backward and forward. I can't train it on this because if it did, it'd waste all the laptop's battery and maybe ruin it. So yeah.
Can you talk about the components of that interface? What are What's it written in, and then the font?
So it was written in Python.
Your GUI.
The GUI. Say that again, please.
What did you use for your GUI? Package, software package.
Coding. Yeah. Made it myself and did this project. It's like getting ideas on like what helps. Yeah.
TK Enter, is that what you use?
Yes. Yeah.
So overall, I thought the report was well written, but I want to go back to where you were saying that you had RGB
Mhm.
and you converted to grayscale. And you said that went from 3D
To 2D.
to 2D. And okay, let's back up. That's a little bit confusing. So you have a physical space that's 2D.
Mhm.
And what generally how we describe this is not in dimensions but in channels. So in RGB you have 3 channels.
Mhm.
When you convert to grayscale, you're going to 1 channel.
Yeah.
Okay, so it's going from 3 channels to 1 channel. Okay, it's kind of nitpicking there, but it was a little bit confusing when you did 3D to 2D. That didn't make a whole lot of sense. The other thing I wanted to ask about is you said that you cropped down from the 424 by 424 to 200 by 200.
Yes.
What criteria did you use to do that cropping? Was this a scaling or was this you were chopping off part of your image?
Yeah, it was scaling.
Scale.
That was the question I was hoping to ask actually was, how did you settle on the 200 by 200 pixel crop? And did you try other sizes to see if you could either improve the accuracy or improve the runtime by running smaller ones?
Well, I'm not sure about that, but it's what the references recommended to do for that.
Might be a good thing to explore in the data set.
Yeah.
You know, you could change the code a little bit
Mhm.
and adjust that on the board. See.
So I was curious. So in the images, it looks sometimes like there might be multiple galaxies. In
Oh,
the
yes.
images,
Yeah.
although some of them, of course, were maybe quite small. So I was curious about kind of your decision to focus on just finding the largest in the image versus trying to detect multiple galaxies, and sort of why you did it that way, and what would happen if you tried to detect multiple galaxies.
Well, first of all, like in the beginning, like without pre-processing the images, there's like sometimes there's more than one galaxy in the image. And that kind of confused the neural network a little bit and getting it wrong sometimes. But yeah, the main focus was just getting the galaxy that was in the middle of the image, and that one was like the biggest one. And if I did more than one, that'd probably mess it up, the neural network. But you probably could do that.
So you said that you only took the images that didn't have any strange things about them, like the bulge or something like that. That's the only thing that you used. Did you try to run your neural network on images that were not, that had something confusing about them and see how it performed?
Yes, but it didn't perform that well in doing that.
So have you thought about if you identify the galaxy in the frame,
Yeah.
and then you blank that area out, make that black, and then search it again? Have Have you thought about looking for the second galaxy that way, or what the opportunity might be? What do you think about that?
Oh, didn't really try that. Because sometimes with the images, like some of the images are like really like blurry and messed up, and so that doesn't really help either. And yeah, some of them are like overlapping the other galaxy, and that didn't really help it.
So when you run your code for that, could you flag those images to say, hey, this really needs a human being to look at it as opposed to a neural net?
Yeah, you could.
Because you could have a fourth output of your neural net of
Mm.
neural network fails, try humans.
I was actually curious, would you be able to, in your GUI, have it let you manually inspect all of the values where it has a low confidence value coming out of the CNN?
Oh, yeah, kind of. Like it like shows the like images and like how confident it was in them, prediction, and yeah, you can look at that, but I don't know if you can change it.
Okay, well, say me as a scientist, if I wanted to look at all of the ones that probably needed human inspection, how would you use the GUI to point those to where those are the first ones I would get a chance to look at?
Probably, yeah, I'm not sure. Well, using programming to do it, but yeah, you could. It's just, I don't know how to do it.
Just curious, as you become more science research, you have astronomy here and then kind of computational neural nets, right?
Yeah.
And if you're going in both directions, what's interesting about astronomy to you that you're getting exposed to the galaxies? What other things in astronomy are kind of cool to you? And then
Well-
also the neural nets. What's kind of other things you can do with neural nets? But what's cool about astronomy? Start with astronomy first.
So it's astronomy, like space, it's like endless, and that is just very cool. And the stars and galaxies are very like bright and beautiful and stuff like that. And then neural nets, you can do many things with that. Like AI is doing crazy stuff nowadays, like AI generated images. And that's actually pretty cool too. It's even funnier when they mess up because it looks weird.
There's a lot of cool things to explore.
Yeah.
And you're in some good dark skies here if you go out and do some
Yeah.
observations yourself too. Even a phone or
So I'm curious, how much you knew about programming at the beginning of the year and or machine learning? And maybe what are the top two things you learned in those areas?
Well, I mean, I knew like the basic fundamentals of programming, but machine learning, not really that much. Like reading books and like articles and sometimes videos that kind of help explain what it is and what it's doing. Yeah.
How do you explain to your classmates what you did?